Welcome to Blue Pen Land here. I'm going to do what I can here to talk about magnetism. Really, these are things you have to see in person, but let's just imagine that you're in my classroom, right? So the first thing I do is I take a petri dish like this, and I float another petri dish on top of it. And on that petri dish, I put a magnet. And as soon as I put enough water in this, that the inside dish is floating, this magnet spins and points itself to north. Points toward the back of my room, which is, of course, north. And, of course, all magnets do this, right? We call the end of the magnet that points toward the North Pole, we call that the North Pole of the magnet, okay? So the North Pole is the pole that points north. And the South Pole is the pole that points toward the South Pole of the Earth. That is our definition of magnets, right? And of course, we know that north attracts south, and south attracts north, and north repels north, and south repels south, right? So this puts us in an interesting thing, right? Interesting pickle, right? So the second thing, is, okay, so how do you tell what's the polarity of a magnet? Well, you can float it on a dish and look at the, which side of the magnet points to the north, which side points to the south. But that takes a lot of doing. So the most convenient way to do it is to find a compass. Okay. Now, if it's a compass in my room, okay, first off, make sure that the compass actually points north, right? Okay, it's got a north and a south, right? Okay, so make sure that it actually points north, because some of my compasses have defected to the other side and they point south, right? But first, ascertain that your compass is not defected, right? And your compass will have a needle on it, right? Usually that's the North Pole and that's the South Pole, right? And then you bring an unknown magnet in, right? We don't know what it is. We don't know what it is, right? Well, if the North Pole, if this end flips around and likes this side, right, then that must be a South Pole magnet. And if the South Pole likes this end, it must be a North Pole magnet, right? Okay, so that's what you do. Now, be careful. Bring it in slowly from the side, okay, because some magnets are strong enough to overwhelm the domains of this needle and just it'll just attract one end of the piece of metal or the other end of the piece of metal, okay? So bring it in from the side and it'll flip around and show its preference, okay? Don't just slap it on top of the thing, right? All right. Now, this is, of course, a shocking revelation. If we're on an Earth, right, and here we are on the Earth, and the North Pole likes what's at the North Pole of the Earth, well, shocking revelation, right? What's up at the North Pole of the Earth is a South Pole magnet, and what's at the South Pole of the Earth is a North Pole magnet. It's a bit like there's a magnet, somewhere deep underneath the Earth, right? And the magnetic field lines go from north to south. So in fact, if you look at a compass needles neatly point in the direction of the magnetic field. Okay, so compass needles, they show you the direction. That's the direction of the magnetic field. Right, and then notice that these lines up here are actually, they show them being parallel to the Earth, but they're actually not. They actually dip into the Earth. So there's a couple of things you got to keep track of with magnetic field lines on the Earth. One of them is dip, and dip is how much it points toward the Earth as opposed to parallel to the Earth's surface. And we define the location of the magnetic pole. It's, of course, below the surface of the Earth, but we'll say that it's, I guess, a surface location is where the dip is straight into the Earth, right? Okay, that would be the South Pole, right? And then where the dip is straight up, right? That would be the North magnetic pole of the Earth, which is kind of crazy, right? So that's a little bit crazy. That'll shake you to your core beliefs. Okay, yeah, there you go. Okay, the Earth's magnetic field, of course, is moving. This is kind of crazy, and it's moving. And it's also kind of diminishing too, okay? And it's moving at a rate that's actually accelerating over time, right? This is what it is. And it's deeply not understood because it's pretty hard to look into the center of the Earth. But basically, it's believed to be the motion of a fluid in the core of the Earth, a molten metal, some deep current, literally but yeah, maybe somebody else knows a little more about it than that. Notice the amount that it's moved, right? In 100 years, it moved that far, right? And in somewhat less than 100 years, in 60 years, it moved that far. So, um, that's interesting, right? We think we're in the middle of a North Pole reversal. The North and South Pole switch places. I think it's like every 700,000 years, but you might want to look that up on Wikipedia. And they actually use that for some kind of dating for archaeology, right? Because if you have a fire, right, and then you have stones next to the fire, these stones can actually retain, this is a fire, right? If you have, the stones will actually retain, if they heat them up hot enough, they'll retain the magnetic field orientation of the Earth. And if you know historically which way the magnetic field is pointed, you can tell when there was fire here, which is kind of cool. And then when you look at maps, you'll see these, that's the true north, right? This is the geographic north or something like that. And that has to do with, what is that? That is, the grid north, sorry. The grid north. And this is an artifact of making the maps. Okay, and then there's also magnetic north, which, is pretty far off, right? This is just one particular quadrangle, and the declination changed from 16.5 to 14 degrees. This is the Sugar House Quadrangle, Salt Lake City area. Okay, I just got this off of someone's PowerPoint, but that's kind of interesting, right? It's decreasing at a rate of 7 minutes of a degree per year, which isn't nothing. Okay, it's not seconds, that's minutes. That's a 60th of a degree. Okay, so so basic concepts of magnetism. Notice that the north repels the north, right? So these guys feel a repulsive force. The South Pole will repel the South Pole, right? And then, of course, the north and the south will attract each other. And I show this with a magnet on the pivot, and then, I hide a magnet in my mouth and pretend that my brain is magnetic. And it's such a good time to be in my class. You poor students. Right. Then I put iron filings on an overhead projector and a single bar magnet under it, and you can see the iron filings are lining up according to these magnetic field lines. Notice that although they haven't drawn these entire loops, maybe this one goes out to Vermont, right? Who knows, right? Notice that all magnetic field lines are loops. And then we use B for the symbol for magnetic field, and that's because there's actually a silent. The British actually sometimes still spell it this way. The real word is magnetism, right? And you can, if you listen to the British when they say it, they're like, magnetism, magnetism. Oh, you can almost hear the B, right? Like that. We tend not to put the B on there ever, but it's a silent B, right? I mean, you really shouldn't be pronouncing it. It's like lamb and comb and stuff like that, right? We don't pronounce that B, right? We don't pronounce, it's not comba, right? Anyway, all B field lines are loops. Okay, this is not true for electric field. Remember, electric field, I could have a positive charge here, and these are just rays. They just go off. If it's an isolated positive charge, those things go off, and they never come back. Okay, but all magnetic field lines are loops. This is, I think, Maxwell's third law. Okay, third equation states that it's basically that. Okay, we can talk about that later. And then the magnetism of a magnet is such that if you break the magnet in half, you'll get 2 bar magnets, each with a south and north pole. Okay, so the magnetism is a bit like the grain of the wood, right? It's like all of these things are like that, and you can keep breaking it down. And I actually did this as a kid. I took a magnet and I kept breaking it because I thought I could make a perpetual motion machine if I had an isolated a magnetic monopole, right? And it's really a shame that I didn't isolate a magnetic monopole, because then I would have, won the Nobel Prize at the age of 7 or something like that, right? Now, the reason that you cannot get a magnetic monopole, a monopole is just a single pole, right? We have electric monopoles. I could have a positive charge, a proton, and just stick it over in Vermont, that's a monopole. It's got only positive charge. But magnetism, you can't have just a north particle, okay? And the reason for this is that if you start to break this down and you keep going smaller and smaller and smaller and smaller, eventually you'll end up with a single iron atom. And that single iron atom has a magnetic pole because it's essentially an electromagnet. The electrons in some way are sort of more going clockwise and anti-clockwise in some statistical sense, right? Because there's no sense that they're really orbiting like planets around a sun, right? but they have a net, the atom itself has a net magnetic moment. And a magnet is basically a bunch of iron atoms where the more magnetic, more atoms are pointed north this way than are pointed south that way, right? Okay, the stronger the magnet is, the more of them, the greater percentage are pointed with north this way and south that way, right? You get down to the individual atom, and of course, where are you going to split the atom, right? As soon as you break up the atom, the electrons aren't in orbit anymore, and there is no magnetic moment. There is no magnetism to the atom then. Okay, yeah. And then notice that in this picture here, right? Notice if we have this, the magnetic field is defined as north to south. It starts at the North Pole, goes to the south. And you remember with the electric field, we said it was positive to negative. Magnetic fields are north to south, and they all are loops. All magnetic fields are loops. And then, the next thing is, how do you pick up something? I understand if you stick a magnet here, right? And I put the North Pole of the magnet there and the South Pole there, these guys would be attracted, and I could pick up other magnets, right? And in fact, if I put this magnet down and it was, south this way and north this way, you discover that as you approached it with the South Pole, that this thing would flip itself around. There'd be a torque on this thing, right? Okay, it would flip around, and that North Pole would go slamming into the South Pole, right? So we can understand how you could pick up a magnet, right? How do you then pick up just a piece of metal, right? If it's not magnetized, well, here's how you do it, right? It's a bit like when we talked about induced charge in electrostatics. If you bring this magnet closer, this magnetic field gets strong enough to induce a magnetic moment in here. Now, let's think about what this means, to induce it. Basically, the atoms, the domains, there's little crystals in here called domains that all tend to point in the same direction, right? These little domains swing around just like compass needles, right? Now let's think about what these magnetic field lines are doing, right? They're going like this. They're going near, right? So near the North Pole magnet, they are coming out, but near the South Pole, they're going in. So in general, the magnetic field lines near the South Pole are going toward the South Pole. Remember, I said that compass needles are a bit like pointers for the magnetic field. So north is the tip of the arrow, south is the tail. So all these little domains are going to point that way. North up on top, south on the bottom, right? So now you've got it's like a magnet. You basically turn iron into a magnet. Now, understand that the south attracts the north, but the south repels the south, right? But the north is closer. So the force of attraction is stronger than the force of repulsion. And so there's a net attractive force. Now, remember, we did this with charge, right? If I had a charged thing, let's say this was positive, and then I had a neutral thing, right? Well, if this is just a neutral thing and we bring this close, right, this is going to be negative on this side and positive on this side, right? The charge, the negative charge will go running, the electrons will run up to this side, and then there will be a net force of attraction between this and this, right? And the force of repulsion will be less because this is farther away, okay? So that's how we can pick things up, right? Now, it has to be a ferrous material, right? Has to be ferromagnetic. That is, ferromagnetic means that it does this. It's got little domains and it can swing around like that. So it's not going to work with, a piece of aluminium or something like that, right? And it won't work with a piece of paper, right, et cetera, et cetera. And I do believe that there are things that are diamagnetic, which it's the opposite. I think it'll flip around the other way. So I think diamagnetic things are repelled by magnets. Better look that one up too. Okay, and then finally, the final basic concept, right, that we must keep in mind is that, remember, electric field, the direction of electric field was from positive to negative. The direction of magnetic field is, wow, funky animation here. The direction of magnetic field is from north to south, okay? So we say that it goes from the North Pole to the South Pole, okay? So magnetic field lines leave the North Pole, enter the South Pole. Just remember this. This will be very helpful when you get to magnetic induction. They leave the North Pole, they enter the South Pole. So if you have a magnet, remember that if you have a pole of a magnet that has field lines coming out of it, it's a magnetic North Pole. If you have magnetic field lines or a magnetic pole that has field lines entering it, it's a magnetic South Pole. I apologize for this video. All right. Thank you. Hope that helps.